At the end of the 19th century, the atom was thought to be the final, indivisible building block of nature. For more than 2,000 years, from the philosophical speculations of Democritus to the refined chemical theories of the modern age, atoms were imagined as the smallest units of matter, solid, unbreakable, eternal. Chemists could combine them, separate them, and rearrange them in reactions, but no one had ever seen inside one. The atom was considered a boundary, a point beyond which inquiry could not pass. Yet science advances precisely at such boundaries, and by the dawn of the 20th century, that ancient certainty began to crack. The story begins with electricity. During the 1800s, experiments with electrical discharge in glass tubes revealed mysterious rays traveling from the negative electrode to the positive electrode. These cathode rays, as they were called, puzzled scientists. Were they waves? Were they particles? The English physicist J. Thomson conducted a series of careful experiments, and in 1897 demonstrated that cathode rays were composed of tiny negatively charged particles. He had discovered the electron. This finding shattered the belief that atoms were indivisible. If atoms contained electrons, then they must have internal structure. Thomson proposed a model in which electrons were embedded within a diffuse cloud of positive charge, like raisins in a pudding. It was an imaginative attempt to explain how negatively charged particles could exist inside a neutral atom. But questions lingered. If the positive charge was spread out evenly, how were electrons arranged? What held them in place? The atomic puzzle was only beginning to unfold. Into this scientific landscape stepped a young physicist from New Zealand, Ernest Rutherford. Rutherford possessed an experimental boldness that set him apart. He was not content with speculation. He wanted evidence. Working first in Canada and later at the University of Manchester, he became fascinated with radioactivity, the strange phenomenon in which certain elements spontaneously emitted energetic particles. These emissions, known as alpha and beta particles, seemed to carry clues about the structure of atoms. Rutherford had already shown that alpha particles were positively charged and relatively massive compared to electrons. He suspected they might serve as probes, tiny projectiles capable of revealing the atom's hidden architecture. If atoms truly resembled Thomson's plum pudding model, then firing alpha particles through a thin sheet of metal should produce only slight deflections. The positive charge, being spread out, would not significantly repel the incoming particles. The experiment seemed straightforward. In 1909, Rutherford's colleagues Hans Geiger and Ernest Marston performed what would become one of the most famous experiments in scientific history. They directed a beam of alpha particles at an extremely thin sheet of gold foil. Surrounding the foil was a fluorescent screen that would flash when struck by an alpha particle. The setup was delicate and precise, requiring patience and careful observation in a darkened room. Most of the alpha particles passed straight through the foil, just as expected, but a small fraction behaved in a way that defied imagination. Some were deflected at large angles. A very few even bounced almost directly backward. It was as though a cannonball had been fired at tissue paper and rebounded toward the shooter. Rutherford later remarked that it was the most incredible event of his life. Such dramatic deflections could not be explained by a diffuse cloud of positive charge. Something much denser had to be at work. Rutherford analyzed the results with characteristic clarity. For an alpha particle to reverse direction, it must have encountered a region of intense positive charge concentrated in a tiny space. The atom, he concluded, was mostly empty space, At its center lay a compact, massive, positively charged core. Around this core, electrons must orbit at relatively great distances. The atom was not a pudding, it was a miniature solar system. This central core would eventually be identified as the nucleus, and within that nucleus resided the particle we now call the proton. Although the term proton was not immediately coined, the essential concept had emerged, a fundamental unit of positive charge concentrated at the heart of every atom. The implications were revolutionary. If atoms were mostly empty space, then the solidity we experience in everyday life was an illusion born of electromagnetic forces. The table beneath your hand feels solid not because its atoms are packed tightly like bricks, but because the electrons in your hand repel the electrons in the table. Matter, at its core, is structured emptiness organized by forces. Rutherford's nuclear model raised new questions. What exactly was this positively charged core made of? How could multiple positive charges coexist so closely without flying apart due to repulsion? And how were electrons arranged around it? The journey to understand the proton had begun, but it was far from complete. In 1917, while continuing his investigations into atomic structure, Rutherford made another breakthrough. By bombarding nitrogen gas with alpha particles, he observed the emission of hydrogen nuclei. He realized that the hydrogen nucleus must be a fundamental building block present in other atoms. This hydrogen nucleus, carrying a single positive charge, was identified as the basic unit of positive electricity. Rutherford had effectively discovered the proton as a distinct particle. The name proton would later be introduced to describe this particle, derived from the Greek word for first. It was a fitting title. The proton was the simplest nucleus, the core of hydrogen, and the fundamental bearer of positive charge in atomic matter. With its discovery, the architecture of the atom became clearer. Each element in the periodic table could be defined by the number of protons in its nucleus. Change that number, and you change the element itself. The discovery of the proton transformed chemistry and physics alike. Previously, elements were distinguished by atomic weight, but atomic weight alone could be misleading because atoms of the same element with different masses existed. The true identity of an element lay in its nuclear charge, the number of protons. This realization led to the modern concept of atomic number, a cornerstone of the periodic table. The proton's positive charge balanced the negative charge of electrons, ensuring that atoms were electrically neutral overall. Yet the proton's mass, far greater than that of the electron, accounted for most of the atom's weight. In the hydrogen atom, the proton alone carries nearly all the mass. Thus, from the earliest stage of its recognition, the proton was understood not merely as a charge carrier, but as a dominant contributor to the substance of matter. The discovery also marked a profound shift in how scientists approached nature. The atom, once considered indivisible, had yielded its secrets under careful experimental assault. This success encouraged further probing into the nucleus itself. If atoms had internal structure, might the nucleus also have layers within layers? Such questions would define the next century of physics. The gold foil experiment became emblematic of scientific courage, the willingness to test assumptions and follow evidence wherever it leads. It demonstrated the power of indirect observation. No one could see the nucleus directly. It was far too small. But by studying how alpha particles scattered, Rutherford inferred its existence. This method, using collisions and scattering to reveal unseen structure, remains central to particle physics today. The discovery of the proton was not a sudden flash of insight, but a gradual unfolding, built upon years of experimental innovation and theoretical reflection. It required advances in vacuum technology, radiation detection, and mathematical analysis. It demanded collaboration among scientists across continents, and it depended on the readiness to abandon cherished models when confronted with contradictory evidence. As the concept of the proton solidified, it reshaped the scientific world. The atom was no longer a philosophical abstraction. It was a measurable, structured entity. Its heart contained concentrated positive charge, defining the identity of matter itself. From hydrogen, the simplest element with 1 proton, to uranium with 90. The diversity of the material world could be traced to variations in this tiny core. The discovery also hinted at deeper mysteries. How could positively charged protons coexist in the nucleus without repelling each other violently? This question would eventually lead to the discovery of the strong nuclear force, a fundamental interaction far more powerful than electromagnetism at short distances. But at the moment of the proton's identification, such forces were still unknown. The nucleus was a new frontier awaiting exploration. Looking back, it is remarkable how quickly the understanding of the atom evolved. Within a few decades, science moved from believing atoms were indivisible to uncovering a structured nucleus with identifiable components. The proton stood at the center of this transformation. It was both a discovery and a revelation, a confirmation that nature's smallest scales are rich with complexity. The journey to the heart of the atom was driven by curiosity, precision, and the courage to question assumptions. The proton emerged not as a mere theoretical construct, but as a measurable, testable reality. It redefined the atom and laid the foundation for nuclear physics, quantum theory, and the technological revolutions that followed. In this unfolding drama, the proton became more than a particle. It became a symbol of scientific progress, a reminder that even the most familiar objects conceal hidden depths. Beneath the surface of ordinary matter lies a concentrated core of positive charge, discovered through persistence and imagination. And from that discovery, a new understanding of the universe began to take shape, one that continues to evolve as we probe ever deeper into the fabric of reality. As the understanding of the hydrogen nucleus deepened, the proton gradually emerged not just as a component of atoms, but as the defining marker of identity in the material universe. The realization that each element is determined by its number of protons transformed the periodic table from a chart arranged by weight into a map organized by fundamental charge. 1 proton meant hydrogen, 2 meant helium, 6 meant carbon. The entire diversity of chemistry unfolded from a simple count of these positively charged cores. Matter, in all its colors, textures, and complexities, was rooted in this numerical simplicity. The implications were profound. If the number of protons determined the nature of an element, then changing that number would transmute one element into another. For centuries, alchemists had dreamed of turning lead into gold. Now, with the discovery of the proton, transmutation was no longer fantasy. It became a question of nuclear structure. Indeed, when Ernest Rutherford first observed hydrogen nuclei emerging from nitrogen under alpha bombardment, he had unknowingly achieved the first artificial nuclear reaction. The age-old dream of transformation had entered the laboratory, yet the proton's story did not end with its identification as hydrogen's nucleus. As experiments continued, physicists realized that atomic nuclei were heavier than could be explained by protons alone. For example, Helium possessed 2 protons, but its mass was roughly 4 times that of hydrogen. Something else had to contribute mass without adding charge. This puzzle led, in 1932, to the discovery of the neutron by James Chadwick. The neutron carried nearly the same mass as the proton, but had no electric charge. Together, protons and neutrons formed the nucleus, bound tightly in a compact structure. The discovery of the neutron clarified why nuclei did not simply explode under electrical repulsion. Although protons repel one another due to their positive charge, neutrons provided additional binding through what would later be understood as the strong nuclear force. The proton was no longer alone in the nucleus. It was part of a partnership, yet its role remained central. Remove or add a neutron, and you create an isotope. Remove or add a proton, and you create a different element entirely. This distinction elevated the proton to a position of special importance. The atomic number, equal to the number of protons, became the true identifier of an element. The periodic table, refined by scientists such as Henry Moseley, confirmed that X-ray frequencies emitted by elements correlated precisely with their proton count. Moseley's work cemented the idea that the nucleus's positive charge, not atomic weight, governed chemical behavior. The proton was the organizing principle behind the table of elements that hangs in classrooms and laboratories around the world. As nuclear physics advanced, the proton revealed both constructive and destructive powers. In stars, protons fuse to release energy. In laboratories, they can be accelerated to extraordinary speeds and smashed into targets, unlocking deeper layers of matter. The development of particle accelerators allowed scientists to probe the proton with increasing precision. By hurling high-energy particles at nuclei, researchers could observe scattering patterns and deduce internal structure. This technique, pioneered in spirit by Rutherford's gold foil experiment, became the cornerstone of high-energy physics. Mid-20th century experiments revealed something astonishing. The proton was not fundamental. Deep inelastic scattering experiments at the Stanford Linear Accelerator in the late 1960s showed that protons contained smaller point-like constituents. These constituents were later identified as quarks. The proton, once thought indivisible, was revealed to be a composite particle. Its interior was a dynamic sea of quarks and gluons interacting through the strong force. This discovery echoed the earlier shattering of atomic indivisibility. Just as the atom had been opened to reveal the nucleus, the proton was opened to reveal quarks. The pattern of scientific progress repeated itself. Each boundary crossed, revealing deeper structure. Facilities such as CERN enabled collisions at energies high enough to glimpse these inner constituents. The proton was no longer a simple sphere of charge, but a vibrant system governed by quantum chromodynamics, the theory describing quark interactions. Despite this deeper understanding, the proton retains a special place in nature. It is remarkably stable. While many subatomic particles decay in fractions of a second, the proton appears to endure indefinitely. Experiments searching for proton decay, predicted by some grand unified theories, have yet to observe such an event. Detectors buried deep underground monitor vast volumes of water or other materials, waiting for a sign that a proton has transformed into lighter particles. So far, the proton's lifetime exceeds 10⁻³ years, far longer than the current age of the universe. This extraordinary stability underpins the persistence of matter. If protons decayed rapidly, atoms would disintegrate, and the universe would look radically different. The fact that protons endure allows galaxies, stars, planets, and living beings to exist over billions of years. Stability at the smallest scale supports continuity at the largest. The proton also plays a crucial role in modern technology. In medical applications, proton beams are used in cancer therapy. By accelerating protons and directing them precisely at tumors, doctors can destroy malignant cells while minimizing damage to surrounding tissue. This technique, known as proton therapy, relies on the unique way protons deposit energy as they slow down in matter. The same particle discovered in early 20th century experiments now contributes to life, saving treatments. In energy research, understanding proton interactions informs efforts in nuclear fusion. Fusion seeks to replicate the processes occurring in the Sun, where protons overcome their mutual repulsion and merge to form helium. Achieving controlled fusion on Earth promises a nearly limitless and clean energy source. The proton thus stands at the center of humanity's hopes for sustainable power. On a more philosophical level, the discovery of the proton reshaped humanity's perception of reality. The world we experience as solid and continuous is, at its foundation, structured by tiny charged particles bound in mostly empty space. The proton embodies the hidden architecture beneath everyday experience. It reminds us that intuition, shaped by humans, scale perception, often fails at microscopic scales. The journey to the heart of the atom has also influenced scientific methodology. Rutherford's boldness, Chadwick's persistence, and the collaborative efforts of countless researchers illustrate how knowledge advances. Instruments grow more sophisticated, theories become more precise, but the essential spirit remains the same: question, test, refine. The proton's discovery was not an isolated event, but part of an ongoing narrative of exploration. Even today, questions remain. Measurements of the proton's radius have yielded puzzling discrepancies depending on the method used. Its internal spin structure continues to challenge physicists, as experiments seek to determine how quark motion and gluon dynamics combine to produce the proton's overall angular momentum. Each answer uncovers new layers of complexity, yet amid these mysteries, the core truth endures. The proton is the defining unit of positive charge in matter. It determines elemental identity, anchors atomic structure, fuels stellar reactions, and supports the stability of the cosmos. From Rutherford's scattering experiments to contemporary particle colliders, the exploration of the proton has driven some of the most transformative discoveries in science. The narrative that began with the shattering of the plum pudding model has evolved into a rich and intricate story spanning more than a century. The proton, once hidden within the atom, now stands illuminated by theory and experiment. It connects the smallest scales of quark interactions to the largest scales of cosmic evolution. In understanding it, we glimpse the unity of physics from the laboratory bench to the burning cores of stars. The journey to the heart of the atom is therefore not merely a chapter in scientific history. It is an ongoing expedition. Each new experiment, each refined measurement, carries forward the legacy of those early pioneers. The proton remains both a foundation and a frontier, a particle whose discovery transformed our understanding of matter and whose mysteries continue to inspire the quest for deeper knowledge. When the proton was first identified as the hydrogen nucleus, it appeared to be a simple, compact particle carrying a single positive charge. For years, it was treated as fundamental, an indivisible unit of matter. It anchored atomic structure, defined the identity of elements, and balanced the negative charge of electrons. But as the 20th century advanced and experimental tools grew more powerful, physicists began to suspect that even this seemingly elementary particle might conceal deeper layers within. The journey inward did not stop at the nucleus. It continued into the proton itself. Early nuclear models described the proton as a tiny, solid sphere of positive charge. This picture was sufficient for explaining basic atomic behavior. However, quantum mechanics was rapidly reshaping scientific understanding. The atom was no longer a miniature solar system governed by classical rules. It was a quantum system defined by probabilities, wave functions, and discrete energy levels. If electrons obeyed quantum laws, what about the proton at the atom's center? Could it truly be structureless? Clues emerged from high-energy experiments in the mid-20th century. As particle accelerators became more sophisticated, scientists gained the ability to hurl electrons and other particles at protons with extraordinary energy. The goal was simple yet profound: probe the proton's interior by observing how incoming particles scattered. This technique echoed the strategy pioneered by Ernest Rutherford decades earlier, when he uncovered the nucleus itself. Once again, scattering would reveal hidden structure. In the late 1960s, experiments at the Stanford Linear Accelerator Center in California delivered a shock. When high-energy electrons struck protons, the scattering patterns suggested that the proton contained smaller, point-like constituents. Instead of behaving like a smooth, uniform object, it acted as though it were composed of discrete internal components. These components were eventually identified as quarks. The quark model had been proposed independently by Murray Gell-Mann and George Zweig in 1964. Initially, quarks were mathematical constructs useful for organizing the growing zoo of subatomic particles discovered in accelerators. But the scattering experiments provided tangible evidence that quarks were not mere abstractions. They were real constituents of matter, residing within protons and neutrons. The proton, it turned out, is composed of 3 primary quarks, 2 up quarks and 1 down quark. Each quark carries a fractional electric charge. The up quark has a charge of +2/3, while the down quark has a charge of 1/3. When combined, 2 ups and 1 down, their charges add up precisely to +1, the proton's total charge. This elegant arithmetic revealed that the proton's positive charge emerges from the sum of its quark constituents. Yet this discovery raised new questions. If quarks carry fractional charges, why are such fractions never observed in isolation? No experiment has ever detected a free quark. They appear to be permanently confined within composite particles like protons and neutrons. This phenomenon is known as confinement, and it is one of the defining features of the strong nuclear force. The strong force is the fundamental interaction responsible for binding quarks together inside protons. Unlike gravity or electromagnetism, the strong force does not weaken with increasing distance in a simple inverse, square manner. Instead, as quarks are pulled apart, the force between them grows stronger, like a stretched rubber band resisting separation. This unique property ensures that quarks remain locked within the proton. The carriers of the strong force are particles called gluons. Gluons act as the exchange messengers between quarks, constantly transmitting the force that binds them. The name gluon reflects their role as the glue of the nucleus, but the picture is far from static. Inside the proton, quarks and gluons are in perpetual motion, interacting in a dynamic, quantum dance. The proton is not a rigid object. It is a seething system of energy and motion. This dynamic behavior is described by the theory of quantum chromodynamics, or QCD. The term chromodynamics refers to color, charge, an abstract property assigned to quarks and gluons. Color charge has nothing to do with visual color. It is simply a convenient label for the types of strong interaction charges. Quarks come in 3 colors, and gluons carry combinations of these. The requirement that particles combine to form color-neutral systems explains why quarks must bind in specific groupings: 3 quarks for baryons like the proton, or quark-antiquark pairs for mesons. Within the proton, the interplay of quarks and gluons is extraordinarily complex. Beyond the 3 primary quarks, there exists a sea of virtual quark-antiquark pairs that briefly pop into existence and annihilate again. These fluctuations arise from the quantum nature of the vacuum itself. Even empty space, at the smallest scales, is not truly empty. It is alive with transient particles that influence the proton's properties. One of the most surprising discoveries about the proton concerns its mass. If one calculates the masses of the 3 quarks inside it, their combined mass accounts for only a small fraction of the proton's total mass. The majority arises from the energy of their interactions, the kinetic energy of moving quarks, and the binding energy of gluons. According to Einstein's principle that energy and mass are equivalent, this energy contributes directly to the proton's mass. In essence, most of the proton's mass is energy confined within its boundaries. The proton's spin presents another layer of mystery. Spin is a quantum property analogous to angular momentum, though it does not correspond to literal spinning in space. For many years, scientists assumed that the proton's spin of 1/2 came simply from the spins of its 3 quarks. However, experiments revealed that quark spins account for only a portion of the total. The remainder must arise from gluon contributions and the orbital motion of quarks within the proton. Deciphering how these components combine remains an active area of research. Modern experiments at facilities such as CERN and Brookhaven National Laboratory continue to probe these questions. By colliding protons at near light speeds, scientists recreate conditions that allow detailed examination of quark and gluon behavior. Each collision produces showers of particles, the traces of which are analyzed to reconstruct the proton's internal dynamics. What emerges from these studies is a portrait of extraordinary complexity. The proton is not a simple trio of quarks orbiting quietly. It is a highly interactive system governed by probabilities and quantum fluctuations. The strong force, mediated by gluons, ensures confinement, while the constant exchange of energy gives rise to measurable properties like mass and spin. The discovery of quark structure did more than redefine the proton. It reshaped the concept of fundamental particles. The standard model of particle physics, developed in the latter half of the 20th century, classifies quarks and leptons as the building blocks of matter. In this framework, the proton is composite rather than fundamental, yet its stability and ubiquity make it one of the most important structures in the universe. Understanding the proton's internal structure also deepens our understanding of matter's stability. The strong force is the most powerful of the fundamental forces at short distances. Without it, quarks would not bind into protons, protons would not bind into nuclei, and atoms would not exist. The delicate balance of forces inside the proton echoes outward, shaping the entire material world. As the journey continues inward, the scale becomes almost incomprehensible. The proton's diameter is about 1 femtometer, 1 quadrillionth of a meter. Within that tiny region unfolds a vibrant interplay of forces and particles. To explore such scales, physicists rely on immense machines, sophisticated detectors, and advanced computational models. The quest to understand the proton's structure pushes technology to its limits, driving innovation in engineering and data analysis. The image that once depicted the proton as a solid bead of positive charge has given way to a far richer vision. It is a bound state of quarks and gluons, governed by quantum chromodynamics, sustained by the strong force, and animated by constant motion. Its properties, charge, mass, spin, emerge from the interplay of deeper constituents. In unveiling this structure, science has once again demonstrated that beneath apparent simplicity lies astonishing complexity. The exploration of the proton's interior is not merely an academic pursuit. It addresses fundamental questions about why matter has the properties it does. Why does it have mass? Why is it stable? Why does it behave consistently across the cosmos? Each answer brings us closer to understanding the architecture of reality itself. Thus, the proton, once thought indivisible, stands revealed as a dynamic microcosm, a universe within a particle. Its quarks and gluons form the foundation upon which atoms, stars, and life are built. And as experiments delve ever deeper into its structure, the proton continues to challenge, inspire, and expand the boundaries of human knowledge. As investigations pushed deeper into the proton's interior, physicists realized that describing it as simply three quarks bound together was an oversimplification. The trio of two up quarks and one down quark defines its basic identity, but the full quantum picture is far richer. Inside the proton exists a constantly shifting environment where quarks exchange gluons. Gluons split into quark-antiquark pairs, and those pairs annihilate back into gluons. This restless activity forms what scientists call the quark-gluon sea. The proton, rather than being a rigid structure, is more like a storm of interacting energy confined within an extraordinarily small region. The mathematical framework governing this behavior is quantum chromodynamics. It is a quantum field theory that describes how quarks interact by exchanging gluons. Unlike photons, which carry the electromagnetic force but do not themselves carry electric charge, gluons possess the very color charge they transmit. This means gluons can interact with one another. The result is a highly nonlinear, self-interacting field that gives rise to confinement. The equations of quantum chromodynamics are elegant, yet notoriously difficult to solve at the energy scales relevant to protons. Much of what is known comes from large-scale computational simulations and high-energy scattering experiments. One of the most fascinating properties of the strong force is asymptotic freedom. At extremely short distances or very high energies, quarks behave almost as if they are free particles, barely interacting with one another. But as they move farther apart, the force strengthens dramatically. This counterintuitive feature explains why quarks cannot be isolated. If one attempts to pull a quark away from a proton, the energy required increases until it becomes sufficient to create a new quark-antiquark pair. Instead of freeing a single quark, the system simply forms new composite particles. Nature prevents quarks from existing alone. Inside the proton, the balance between confinement and asymptotic freedom produces a dynamic equilibrium. Quarks move at relativistic speeds, their kinetic energy contributing significantly to the proton's overall mass. The gluons binding them are not static connectors but active participants, carrying momentum and spin. In fact, Experimental evidence suggests that gluons contribute a substantial portion of the proton's total spin. This realization emerged from decades of spin, polarized scattering experiments conducted at facilities such as Brookhaven National Laboratory. These studies revealed that the simple addition of quark spins accounts for only part of the proton's angular momentum. The rest arises from gluon spin and the orbital motion of quarks and gluons swirling inside. The internal motion within the proton challenges classical intuition. There are no fixed orbits, no tiny billiard balls circling neatly. Instead, there are probability distributions described by wave functions. The position and momentum of quarks are not simultaneously definite. They are governed by the uncertainty principle. The proton's structure is therefore best understood statistically. Physicists speak of Parton distribution functions, mathematical descriptions of how momentum is shared among quarks and gluons. These distributions shift depending on the energy scale at which the proton is probed. At higher energies, the quark-gluon sea becomes more prominent, revealing layers of complexity invisible at lower energies. Another puzzle that continues to intrigue scientists is the proton radius problem. For decades, measurements of the proton's charge radius derived from electron scattering experiments agreed within a narrow range. However, when researchers measured the radius using muonic hydrogen, in which a muon replaces the electron, they obtained a significantly smaller value. This discrepancy sparked intense debate and further experiments, including investigations at CERN. While recent results have brought measurements closer together, the episode illustrates how even seemingly well-understood properties of the proton can conceal surprises. The proton's internal structure also plays a crucial role in nuclear interactions. When protons and neutrons bind together in nuclei, it is ultimately the residual strong force, an extension of quark-gluon interactions, that holds them together. This residual force arises because protons and neutrons themselves are composite particles. Their quark structures allow for interactions that resemble a spillover of the strong force beyond individual nucleons. Without this mechanism, atomic nuclei would not form, and matter as we know it would not exist. At extremely high temperatures and densities, such as those present microseconds after the Big Bang, protons and neutrons did not exist as bound states. Instead, the universe was filled with a quark-gluon plasma, a hot, dense soup in which quarks and gluons moved freely. Experiments recreating these conditions are conducted in heavy, ion collisions at accelerators. When nuclei are smashed together at near light speeds, detectors observe fleeting glimpses of this primordial state. These studies help scientists understand how protons first emerged as the universe cooled, and quarks became confined into stable particles. The proton's structure also influences precision tests of fundamental symmetries. Tiny differences in how quarks are distributed can affect scattering cross, sections, and decay rates. By comparing experimental results with theoretical predictions, physicists test the boundaries of the standard model. Any deviation could signal new physics beyond the current framework. Thus, the proton serves not only as a subject of study, but also as a testing ground for deeper laws. Despite its complexity, the proton exhibits remarkable consistency. Every hydrogen nucleus in the observable universe is identical. Whether in a distant galaxy or within a drop of water on Earth, protons share the same mass, charge, and intrinsic properties. This uniformity underpins the universality of physical laws. It means that the same chemistry operates across cosmic distances. The same nuclear reactions power stars everywhere. The proton's internal structure, governed by quantum chromodynamics, is replicated billions upon billions of times throughout the cosmos. Technological advances continue to refine our understanding. The upcoming electron-ion collider, planned in the United States, aims to provide unprecedented insight into the proton's three-dimensional structure. By colliding polarized electrons with polarized protons, researchers hope to map the distributions of quarks and gluons with extraordinary precision. These experiments promise to reveal how internal motion generates observable properties, and how confinement emerges from the underlying equations. The journey into the proton is a journey into the heart of quantum reality. It reveals that mass is not simply a sum of constituent parts, but a manifestation of energy and interaction. It shows that stability arises from dynamic balance rather than rigid structure. It demonstrates that even the smallest building blocks contain layers of activity beyond ordinary perception. From the early days when the proton was considered indivisible to the present era of quark-gluon exploration, the evolution of understanding reflects the broader arc of modern physics. Each deeper probe uncovers richer structure. Each refined measurement sharpens theoretical insight. And yet, the proton remains stable and enduring, a cornerstone of matter whose internal turbulence gives rise to the calm solidity of the macroscopic world. In contemplating the proton's structure, one confronts a paradox: profound complexity confined within extraordinary simplicity. A single positive charge, identical everywhere, emerges from an intricate web of quark and gluon interactions. The proton is at once a composite system and a fundamental pillar of existence. Its internal dynamics echo through the fabric of atoms, nuclei, stars, and galaxies. By uncovering its structure, science has illuminated not only the heart of the atom, but also the deep principles that govern the universe itself. When we hold a stone in our hand, step onto the ground, or feel the weight of our own body, we are experiencing mass in its most familiar form. Mass feels solid, tangible, and permanent. Yet if we travel inward past molecules, past atoms into the nucleus, we discover that most of this mass is concentrated in protons and neutrons. And if we focus specifically on the proton, we encounter one of the most astonishing revelations in modern physics. The proton's mass does not come primarily from the mass of its constituent particles, it emerges from energy itself. At first glance, the proton seems straightforward. It is composed of 3 quarks, 2 up quarks and 1 down quark. If one were to assume that the proton's mass is simply the sum of the masses of these quarks, the explanation would appear complete. But measurements tell a different story. The quarks inside a proton account for only a small fraction of its total mass. The rest, nearly all of it, arises from the energy of their interactions. To understand this, we must recall Einstein's revolutionary insight expressed in the equation E=mc2. Energy and mass are not separate entities. They are interchangeable forms of the same physical reality. Energy confined within a system contributes to that system's mass. In the case of the proton, the quarks are bound together by the strong nuclear force, mediated by gluons. The energy associated with this binding, along with the kinetic energy of quarks moving at relativistic speeds inside the proton, manifests as mass. The proton is therefore not a simple container of 3 tiny particles. It is a dynamic, vibrating system in which quarks and gluons interact continuously. These interactions generate enormous energy on microscopic scales. That energy, confined within a region roughly 1 femtometer across, gives rise to the proton's mass. In other words, most of the mass of ordinary matter is energy held in place by the strong force. This realization reshapes our understanding of the material world. When we consider the weight of a mountain or the density of a planet, we are ultimately considering energy locked inside protons and neutrons. The visible universe owes its mass largely to the restless motion and interaction of quarks bound by gluons. Matter is not fundamentally heavy because its constituents are heavy. It is heavy because of the energy of their confinement. The strong force, described by quantum chromodynamics, plays the central role in this process. Unlike electromagnetism or gravity, the strong force becomes stronger as quarks are pulled apart. This confinement ensures that quarks remain bound within protons and neutrons. The energy required to separate them increases rapidly, and that energy contributes directly to mass. The more tightly confined the quarks, the greater the energy stored within the proton. Experimental evidence supporting this picture has come from high-energy particle collisions. When protons are smashed together at facilities such as CERN, detectors analyze the resulting particle showers. These collisions reveal how quarks and gluons share momentum and energy inside the proton. They confirm that gluons, massless carriers of the strong force, carry a significant portion of the proton's internal energy. Even though gluons themselves have no rest mass, the energy they transmit in exchange contributes to the proton's total mass. This insight carries profound philosophical implications. For centuries, mass was regarded as an intrinsic property of matter, a measure of how much stuff an object contained. Modern physics reveals that mass can arise from interactions rather than substance. The proton's mass is not merely the sum of tiny solid pieces. It is the outcome of dynamic relationships governed by quantum laws. The proton's mass also influences the stability of atoms. Because protons are nearly 0 times heavier than electrons, they dominate the mass of atoms. Electrons, though crucial for chemistry, contribute very little to an atom's weight. Remove the electrons from a hydrogen atom, and its mass remains almost unchanged. The heavy core of the atom lies in its protons and neutrons, whose mass is rooted in strong force energy. Another layer of understanding emerges when we consider the role of the Higgs field. The discovery of the Higgs boson at CERN confirmed that fundamental particles acquire mass through interactions with the Higgs field. Quarks gain their small intrinsic masses in this way. However, these intrinsic masses are tiny compared to the proton's overall mass. The Higgs mechanism provides only a small fraction of what we observe. The dominant contribution comes from the strong force energy binding the quarks together. This distinction is subtle but crucial. The Higgs field explains why quarks have mass at all, but it does not account for the majority of the proton's mass. That majority arises from quantum chromodynamics, the dynamic energy of confinement. The proton is thus a vivid example of how different fundamental forces cooperate to shape reality. The implications extend to cosmology. In the early universe, shortly after the Big Bang, temperatures were so high that quarks and gluons existed freely in a quark-gluon plasma. As the universe expanded and cooled, quarks became confined within protons and neutrons. At that moment, much of the universe's mass effectively came into being, not because new matter was created, but because energy became trapped in bound states. The emergence of protons marked a turning point in cosmic history, enabling the formation of nuclei, atoms, stars, and galaxies. The proton's mass also sets the scale for nuclear reactions. In stars, protons fuse to form heavier elements, releasing energy in the process. The delicate balance between mass and energy determines how much energy is released during fusion. The difference in mass between initial and final products appears as radiant energy, powering stars like our Sun. Thus, the proton's mass is not only a measure of confinement energy, but also a key factor in stellar evolution. Precision measurements continue to refine our knowledge of the proton's mass. It is known to extraordinary accuracy, yet researchers seek ever greater precision to test theoretical predictions. Even slight discrepancies could hint at physics beyond the standard model. The proton, though stable and well studied, remains a window into deeper layers of reality. Perhaps the most remarkable aspect of this story is how it overturns common intuition. When we think of mass, we imagine solidity and substance. But at the deepest level, mass is a manifestation of motion and interaction. The proton's interior is not static. Quarks move at speeds approaching that of light, exchanging gluons in an intricate pattern described by probability amplitudes. The energy of this motion, multiplied by Einstein's constant C2, becomes the mass that anchors matter. In every atom around us, protons sit at the center, their mass dominating the atom's total weight. Multiply that mass by the staggering number of atoms in a human body, and you find that your physical presence, your weight on a scale, is largely the energy of quarks bound by gluons. The solidity of the world is, at its core, a testament to the power of the strong force. The journey to understand the proton's mass has required decades of experimental ingenuity and theoretical innovation. It has linked quantum mechanics with relativity, particle physics with cosmology. It has revealed that energy and mass are intertwined in ways that defy classical imagination. And it has shown that the simplest particle in the nucleus conceals a profound truth. Matter's weight arises not merely from its ingredients, but from the vibrant energy that binds them together. Thus, when we ask why matter has weight, the answer leads us inward to the proton. Its mass is not a simple attribute, but a dynamic achievement of quantum forces. Within its tiny boundary lies the energy that gives substance to the universe. Every object, every planet, every living being owes its heft to this confined energy. The proton, though minuscule, carries the power that makes matter real. Charge is one of the most fundamental properties in all of physics. It shapes how particles interact, how atoms form, how molecules bond, and how matter behaves at every scale. At the heart of this intricate balance stands the proton, carrying a single positive electric charge. That charge may seem like a simple numerical value, but its precision and stability are essential to the existence of the universe as we know it. Without the proton's exact charge and remarkable durability, atoms would not hold together, chemistry would collapse, and life would be impossible. Every proton carries a charge of +1 in natural units, equal in magnitude and opposite in sign to the electron's one charge. This equality is not approximate. It is exact to the limits of experimental measurement. The balance between these charges ensures that atoms are electrically neutral overall. In a hydrogen atom, a single negatively charged electron orbits a single positively charged proton. The electromagnetic attraction between them binds the atom together. If the proton's charge were even slightly different, the strength of that attraction would change, altering atomic structure in profound ways. The electromagnetic force, governed by this balance of charges, operates according to precise mathematical laws. Opposite charges attract, like charges repel. Inside the nucleus, protons sit extremely close to one another, each carrying positive charge. By the rules of electromagnetism alone, they should repel violently and fly apart, yet they do not. This apparent contradiction reveals the presence of another force, the strong nuclear force, which overcomes electrical repulsion at very short distances. The proton's charge, therefore, exists in a delicate interplay with deeper forces that maintain stability. This stability is not merely a local feature of atomic nuclei. It is a universal principle. The consistency of the proton's charge across all space and time underpins the reliability of physical laws. Whether in a distant galaxy or a laboratory on Earth, a proton behaves the same way. Its charge does not fluctuate. It does not weaken. It does not decay. This constancy allows the equations of electromagnetism, first unified by James Clerk Maxwell, to describe phenomena with extraordinary precision. From the glow of distant stars to the flow of electricity in our homes, the predictable behavior of charge makes modern technology and scientific understanding possible. The equality between proton and electron charge is especially striking. The electron, discovered by J. Thomson, is far lighter than the proton, nearly 0.0 times less massive, yet its charge perfectly balances that of the proton. This symmetry ensures that atoms can exist in stable configurations. If the electron's charge were even slightly different from the proton's, neutral atoms would not form as they do. The resulting imbalance would produce electric forces that dominate matter on large scales, preventing the formation of stars, planets, and biological structures. Inside the nucleus, the story becomes even more dramatic. Multiple protons are confined within a space so small that their positive charges generate intense repulsive forces. The strong nuclear force must be powerful enough to overcome this repulsion and bind protons together with neutrons. The balance between electromagnetic repulsion and strong force attraction determines which nuclei are stable and which are radioactive. Light elements like helium are stable because the strong force sufficiently counteracts the electrical repulsion. Heavier elements require increasing numbers of neutrons to maintain stability. Beyond a certain size, the balance fails, leading to radioactive decay. This interplay shapes the entire periodic table. The number of protons defines the element, but the stability of that element depends on the careful balance of forces within the nucleus. In stars, this balance governs nuclear fusion. Protons must overcome their electrical repulsion to fuse into helium. The extreme temperatures and pressures inside stellar cores provide the necessary energy. Once fusion begins, the resulting energy powers the star, producing light and heat. Thus, even the sunlight that warms our planet is tied to the delicate balance between charge and nuclear forces. The proton's stability is equally critical. Unlike many subatomic particles that decay in fractions of a second, the proton appears to be extraordinarily long-lived. Experiments searching for proton decay, conducted in massive underground detectors, have yet to observe such an event. The proton's lifetime is estimated to exceed 10 years, vastly longer than the current age of the universe. This stability ensures that matter persists over cosmic timescales. If protons decayed readily, atoms would disintegrate, and the material universe would gradually dissolve. Some grand unified theories predict that protons may eventually decay, linking the electromagnetic, weak, and strong forces into a single framework. Detecting such decay would revolutionize physics. Facilities around the world monitor enormous volumes of water or other materials, watching for the faint signatures of proton transformation. So far, the proton has remained steadfast. Its apparent permanence supports the continuity of galaxies, stars, and life itself. On Earth, the proton's charge plays a central role in chemistry. Chemical bonds arise from interactions between electrons and nuclei. The positive charge of the nucleus attracts electrons, forming stable atomic orbitals. When atoms approach one another, their electrons rearrange to create molecules. The properties of water, the structure of DNA, the folding of proteins, all depend on electromagnetic interactions ultimately rooted in the proton's charge. Electricity, magnetism, and light also trace their origins to charge. When protons and electrons move, they create electric currents and magnetic fields. The flow of electrons in a conductor is influenced by the positive charges fixed within atomic nuclei. In this sense, the proton's charge provides the stable framework within which electrical phenomena occur. Modern civilization, powered by electrical grids, communication systems, and electronic devices, rests upon the predictable behavior of charged particles. The precision of the proton's charge invites deeper questions. Why is it exactly equal and opposite to the electrons? Why does it have the value it does? These questions touch on fundamental symmetries in nature. The standard model of particle physics incorporates electric charge as a basic property of quarks and leptons, but it does not fully explain why the charges take their specific values. The proton's charge emerges from the combination of its constituent quarks, 2 up quarks and 1 down quark, whose fractional charges add to +1. Yet the reason for this exact arrangement remains an open mystery. Despite such unanswered questions, the observable consequences are clear. The proton's charge provides the scaffolding of matter. It allows atoms to form and remain stable. It ensures that electromagnetic forces operate with consistent strength. It participates in the nuclear balance that determines the life cycles of stars. And through its extraordinary longevity, it guarantees that the structures built from atoms endure for billions of years. Imagine, for a moment, a universe in which the proton's charge were slightly weaker. Electrons would bind less tightly to nuclei. Atoms might become fragile, easily ionized. Chemical reactions would differ dramatically. Or imagine a stronger charge, intensifying attraction and repulsion alike. The balance within nuclei might shift, altering the abundance of elements forged in stars. Small changes at the level of charge could cascade into vast differences in cosmic evolution. Thus, the proton's charge and stability are not trivial details. They are foundational constants shaping reality. They represent a fine balance among forces that permit complexity to arise. The calm stability of everyday matter is built upon a subtle equilibrium maintained at unimaginably small scales. In the end, the proton's positive charge is more than a numerical value. It is a cornerstone of structure, a guarantor of stability, and a bridge between the microscopic and macroscopic worlds. Its unwavering presence binds electrons into atoms, atoms into molecules, and molecules into the rich tapestry of matter we observe. Through the precise balance of charge and the remarkable endurance of its existence, the proton sustains the architecture of the universe. At the center of every atom lies a nucleus, and at the center of that nucleus are protons. If electrons define the outer character of an atom, its chemistry, its bonding behavior, its visible interactions, then protons define its identity. The architecture of atoms begins with the number of protons embedded in the nucleus. change that number, and you do not merely alter a property, you transform the element itself. In this way, protons are the true architects of the material world. The simplest atom, hydrogen, contains a single proton in its nucleus. That lone proton determines that hydrogen is hydrogen, no more, no less. Add another proton, and you no longer have hydrogen, you have helium. Continue adding protons, and you move step by step through the periodic table. 6 protons produce carbon, the backbone of organic chemistry. 8 create oxygen, essential for respiration. 26 produce iron, the core element of planetary interiors and human blood. 92 produce uranium, a heavy element capable of releasing immense nuclear energy. The number of protons, known as the atomic number, is the defining fingerprint of every element in the universe. This realization transformed science in the early 20th century. Before the internal structure of the nucleus was fully understood, elements were often arranged by atomic weight. But atomic weight alone could be misleading due to the existence of isotopes, atoms, with the same number of protons, but different numbers of neutrons. It was the work of researchers like Henry Moseley that confirmed the central importance of proton count. By measuring X-ray frequencies emitted by different elements, Moseley demonstrated that atomic number, not mass, determined elemental identity. The periodic table was reorganized accordingly, and protons took their rightful place as the structural foundation of chemistry. Inside the nucleus, protons do not exist alone. They share space with neutrons, particles of nearly equal mass but no electric charge. Together, protons and neutrons are known as nucleons. The arrangement and ratio of these nucleons determine the stability of the nucleus. For light elements, a roughly equal number of protons and neutrons ensures stability. As elements grow heavier, additional neutrons are required to counterbalance the increasing electrical repulsion between positively charged protons. This repulsion is a central challenge of nuclear architecture. Each proton carries a positive charge, and like charges repel. If electromagnetism were the only force at work, nuclei would fly apart instantly. Yet they do not, because the strong nuclear force binds nucleons together at extremely short distances. This force is powerful enough to overcome electromagnetic repulsion within the confined space of the nucleus. The delicate balance between these forces shapes which nuclei are stable and which are prone to radioactive decay. Radioactivity itself reveals the tension within heavy nuclei. When too many protons crowd together, the strong force can no longer fully counteract their mutual repulsion. The nucleus may emit particles or radiation in an attempt to reach a more stable configuration. Alpha decay, for instance, involves the emission of 2 protons and 2 neutrons bound together as a helium nucleus. Through such processes, unstable elements gradually transform into more stable ones. The architecture of the atom is therefore dynamic, capable of change under certain conditions. The proton's role in nuclear architecture also extends to the formation of isotopes. Atoms of the same element share the same number of protons, but may differ in neutron count. Carbon, for example, always contains 6 protons, but carbon-12 has 6 neutrons, while carbon-14 has 8. These differences affect nuclear stability, but not chemical behavior. Because chemical reactions depend primarily on electron configurations, which are determined by proton number, carbon isotopes behave similarly in chemistry despite differing nuclear masses. The influence of protons extends beyond atomic identity into atomic size and electron arrangement. The positive charge of the nucleus attracts negatively charged electrons. The greater the number of protons, the stronger the nuclear attraction experienced by electrons. This attraction influences atomic radius, ionization energy, and overall chemical reactivity. As one moves across the periodic table, increasing proton number pulls electrons closer, reducing atomic size and altering bonding patterns. Thus, the proton shapes not only the identity of elements, but also their chemical personalities. In the vast furnaces of stars, protons again define architecture on a grand scale. Stellar nucleosynthesis begins with hydrogen nuclei single protons. Through nuclear fusion, protons combine to form helium and, in more advanced stages of stellar evolution, heavier elements. Each fusion step changes the proton count within nuclei, creating new elements. The architecture of matter in the universe is therefore built in stellar cores, one proton at a time. Without protons, there would be no pathway from hydrogen to carbon, oxygen, and beyond. The architecture determined by protons also governs nuclear energy. In fission reactions, heavy nuclei such as uranium split into smaller nuclei with fewer protons. The rearrangement of protons and neutrons releases energy due to differences in nuclear binding energy. In fusion reactions, light nuclei combine, again altering proton arrangements and releasing energy. In both cases, the configuration of protons within nuclei dictates the outcome. Nuclear power plants and experimental fusion reactors rely on these rearrangements of atomic architecture. Even the forces that shape planetary bodies connect back to protons. The density of matter, influenced by nuclear mass, determines how planets form and differentiate. Iron, with 6 protons per nucleus, plays a key role in Earth's core. The architecture of atoms, rooted in proton number, influences large-scale geological processes. In this way, the proton's presence in nuclei echoes outward to shape landscapes and magnetic fields. The remarkable feature of atomic architecture is its universality. A carbon atom on Earth is identical in proton count to a carbon atom in a distant galaxy. This uniformity allows astronomers to analyze the light from stars and determine their composition. Spectral lines correspond to electron transitions, which in turn depend on proton number. By studying starlight, scientists identify elements billions of light years away. The proton's role in atomic identity thus becomes a tool for exploring the cosmos. The architecture of atoms also enables the complexity of life. Carbon's 6 protons create an electron configuration that supports versatile bonding. Oxygen's 8 protons produce the chemical properties necessary for respiration. Nitrogen's 7 protons allow the formation of amino acids and nucleotides. The biological world depends on a specific range of proton-defined elements. If the architecture of atomic nuclei were different, life as we know it might not exist. Inside the nucleus, protons occupy quantized energy levels, somewhat analogous to electrons in atomic orbitals. The nuclear shell model describes how nucleons arrange themselves in discrete states. Certain magic numbers of protons and neutrons produce especially stable nuclei. These patterns reveal that nuclear architecture is not random but governed by underlying quantum principles. The proton participates in this structured arrangement, contributing to the stability or instability of the nucleus. The concept of atomic architecture also underscores the layered nature of matter. Molecules are built from atoms, atoms from nuclei and electrons, nuclei from protons and neutrons, and protons from quarks and gluons. At each level, structure arises from interactions governed by fundamental forces. The proton occupies a pivotal layer in this hierarchy. It bridges the world of quarks with the world of chemistry, serving as the anchor around which atomic systems are organized. From the smallest hydrogen atom to the heaviest naturally occurring element, the architecture of matter is traced back to the proton. It defines identity, influences stability, shapes chemical behavior, and enables cosmic evolution. The simple count of protons within a nucleus determines the richness of the periodic table and the diversity of the universe. In contemplating atomic architecture, we see how a tiny particle governs immense complexity. The proton's presence in the nucleus is not merely a structural detail. It is the blueprint of matter itself. Through its charge, mass, and position within the nucleus, the proton shapes the structure of atoms and, by extension, the structure of everything built from them. From the air we breathe to the stars that shine above, the architecture of existence rests upon the quiet, persistent presence of protons at the heart of every atom. In the early decades of the 20th century, physics stood at a dramatic crossroads. Classical mechanics, perfected by Isaac Newton, and electromagnetism, unified by James Clerk Maxwell, had created a picture of the universe that seemed nearly complete. The world appeared deterministic, continuous, and governed by precise mathematical laws. Yet beneath this confidence, cracks were forming. Experiments on radiation, atomic spectra, and the stability of matter stubbornly resisted classical explanation. The old framework could predict the motion of planets and projectiles, but it failed to account for how atoms emitted light or why matter did not collapse under its own electromagnetic forces. It was in this atmosphere of conceptual tension that a new revolution unfolded, one that would culminate in a radically different understanding of reality. At the heart of this transformation was the growing realization that energy behaved in ways classical theory could not explain. When scientists studied how heated objects emitted radiation, what became known as blackbody radiation, they encountered a catastrophic mismatch between prediction and observation. Classical theory predicted that energy emitted at high frequencies should grow without bound, a result famously called the ultraviolet catastrophe. But experiments showed that the intensity of radiation peaked at a certain frequency and then declined. The mathematics of continuity had led to absurd infinity. Something was fundamentally wrong. The first decisive step toward resolution came from Max Planck, who proposed that energy is not emitted or absorbed continuously, but in discrete packets, later called quanta. This idea, introduced in 1900, was initially a mathematical trick, a desperate solution to fit experimental data. Yet its implications were profound. Planck's constant, denoted by h, set a fundamental scale to physical processes. Energy was proportional to frequency, E equals hf. With this equation, the ultraviolet catastrophe vanished. Nature, it seemed, operated in steps, not in a smooth flow. However, the full meaning of quantization did not become clear until a few years later, when Albert Einstein extended the idea. In 1905, he proposed that light itself behaves as if it consists of discrete particles, light quanta, later called photons. His explanation of the photoelectric effect showed that light's energy depends on frequency, not intensity. This contradicted the classical wave picture of light and suggested a dual character. Light was both wave and particle. Einstein's work deepened the crisis. If light could behave like matter, and matter exhibited wave, like patterns, then the boundary between substance and radiation blurred. The atomic model also demanded revision. Niels Bohr introduced a quantum model of the atom in 1913, proposing that electrons orbit the nucleus only in specific, quantized energy levels. They could jump between levels by emitting or absorbing photons of precise energy. Bohr's model successfully explained the spectral lines of hydrogen, offering powerful confirmation of quantum ideas. Yet his model still relied partly on classical orbits and could not fully account for more complex atoms. The true conceptual leap occurred in the mid-1920s. Werner Heisenberg formulated matrix mechanics, focusing strictly on observable quantities. Around the same time, Erwin Schrödinger developed wave mechanics, describing particles through a wave equation that governed probability amplitudes. These approaches were mathematically equivalent, but conceptually revolutionary. Instead of precise trajectories, electrons were described by wave functions, mathematical entities encoding probabilities. The deterministic clockwork of Newton gave way to inherent uncertainty. This shift was crystallized in Heisenberg's uncertainty principle. It states that certain pairs of physical properties like position and momentum cannot both be known with arbitrary precision. The more accurately one is measured, the less precisely the other can be determined. This was not due to experimental imperfections, but a fundamental feature of nature. Reality itself had limits on knowledge. The observer was no longer detached from the system. Measurement influenced outcome. Schrödinger's equation provided a powerful tool for predicting how quantum systems evolve over time. Yet its probabilistic interpretation, clarified by Max Born, revealed a startling philosophical implication. Physics could no longer predict individual events with certainty, only probabilities. The future of a single particle was not predetermined. Only statistical distributions were knowable. This marked a profound departure from classical determinism. The philosophical debate that followed was intense. Einstein resisted the abandonment of determinism, famously remarking that God does not play dice. Bohr and his colleagues, advocating what became known as the Copenhagen interpretation, argued that quantum mechanics was complete. According to this view, physical systems do not possess definite properties until measured. The act of observation collapses the wave function into a definite state. Reality at the microscopic scale is not simply hidden. It is fundamentally indeterminate. Despite conceptual unease, quantum mechanics proved extraordinarily successful. It explained atomic structure, chemical bonding, and the behavior of solids. The development of quantum field theory extended these principles to describe particle interactions and electromagnetic forces with astonishing accuracy. Quantum electrodynamics became one of the most precisely tested theories in history. The mathematics predicted experimental results to many decimal places, far surpassing classical approximations. The implications extended beyond physics into technology. Semiconductors, lasers, and nuclear energy all rely on quantum principles. Modern electronics, from transistors to integrated circuits, function because electrons occupy quantized energy bands in solids. Without quantum mechanics, there would be no digital revolution. What began as a solution to a radiation problem became the foundation of the modern technological world. Yet the conceptual puzzles remain unresolved. Quantum entanglement, described by Einstein as spooky action at a distance, reveals correlations between particles that persist across vast distances. Experiments inspired by Bell's theorem have confirmed that these correlations cannot be explained by local hidden variables. Nature violates classical intuitions about separability and locality. Entangled systems behave as unified wholes, even when spatially separated. This raises profound questions about the nature of reality. Is the wave function merely a mathematical tool, or does it represent something physically real? Interpretations abound, many: worlds, pilot wave theory, objective collapse models. Each attempts to reconcile the formalism with philosophical coherence. Yet none has definitively resolved the measurement problem. Quantum mechanics works flawlessly in practice, but its meaning remains contested. As the 20th century progressed, quantum theory merged with relativity in quantum field theory, and efforts began to unify it with gravity. The quest for a theory of quantum gravity continues. Approaches such as string theory and loop quantum gravity attempt to reconcile the discrete with the geometric curvature of spacetime described by Einstein. The challenge is immense because quantum mechanics describes probabilities on fixed spacetime backgrounds, while general relativity treats spacetime itself as dynamic. Their mathematical frameworks are profoundly different. The intellectual journey from classical certainty to quantum probability transformed not only physics, but our conception of knowledge. Classical science portrayed a universe governed by continuous laws, predictable in principle. Quantum theory revealed limits to predictability and introduced fundamental discreteness. It shifted emphasis from trajectories to amplitudes, from certainties to probabilities, from detached observation to participatory measurement. This transformation reshaped philosophy as much as science. Questions about realism, determinism, and causality gained renewed urgency. Is reality independent of observation? Are probabilities fundamental or epistemic? Does the universe branch into multiple histories? These debates continue to animate both physicists and philosophers. In summary, the sixth stage of this scientific revolution represents the consolidation and deepening of quantum mechanics into a mature, though philosophically challenging, framework. It established probability as a core principle of nature, revealed intrinsic limits to measurement, and laid the groundwork for technologies that define modern civilization. At the same time, it left open fundamental questions about the ultimate nature of reality. The revolution that began with Planck's quantized energy had, by mid-century, redefined our understanding of existence itself. The exploration of the proton ultimately leads scientists beyond the present understanding of matter into the future of physics itself. While the proton has been studied for more than a century, it continues to challenge theoretical models and experimental techniques. The seventh stage of this scientific journey looks forward, asking what the proton can reveal about the fundamental laws of nature, the unification of forces, and the ultimate structure of reality. In this sense, the proton is not only a discovered particle, but also a guide toward future discoveries. Modern physics stands on the foundation of the Standard Model of particle physics, a framework that successfully describes most known particles and forces except gravity. The development of this model was shaped by contributions from many physicists, including Murray Gell-Mann, who helped develop the quark model, and Steven Weinberg, who worked on electroweak unification. The Standard Model describes the proton not as a fundamental particle, but as a composite system made of quarks and gluons interacting through the strong nuclear force. Yet despite its success, the Standard Model is incomplete. Questions about dark matter, dark energy, and gravity remain unanswered. The proton, as one of the most precisely studied particles, serves as a testing ground for new theories that go beyond current physics. One of the most important future questions concerns the possible decay of the proton. Some grand unified theories predict that protons may eventually decay into lighter particles. If this were observed, it would provide evidence that the electromagnetic, weak, and strong forces are different manifestations of a single unified force at extremely high energies. Large underground detectors are built to search for this phenomenon. For example, experiments conducted at facilities such as CERN and other international research collaborations continuously monitor vast volumes of matter for signs of proton decay. So far, no definitive decay event has been observed. This suggests that the proton's lifetime may exceed 10 years, far longer than the age of the universe. The extraordinary stability of the proton remains both reassuring and mysterious. Future physics also seeks to map the internal three-dimensional structure of the proton with unprecedented precision. Traditional experiments treated the proton as a two-dimensional distribution of charge and momentum. Newer research aims to visualize how quarks and gluons move inside the proton in space and time. One major project dedicated to this goal is the proposed electron-ion collider in the United States. This facility will collide polarized electrons with polarized protons, allowing scientists to study spin structure, momentum distribution, and quantum correlations with exceptional detail. Spin remains one of the great mysteries of proton physics. The proton has an intrinsic quantum spin of 1/2, but experiments have shown that the spin of its three valence quarks accounts for only a portion of the total value. The rest comes from gluon spin and the orbital motion of quarks and gluons inside the proton. Understanding how these components combine remains an active research problem. Solving this puzzle could reveal deeper insights into quantum chromodynamics, the theory describing the strong force. Another important frontier involves the relationship between the proton and cosmology. In the earliest moments after the Big Bang, the universe existed as a hot plasma of quarks and gluons. As the universe expanded and cooled, quarks became confined into protons and neutrons. This transition shaped the formation of all visible matter. Understanding how protons formed in the early universe helps scientists model cosmic evolution and the distribution of matter across galaxies. Observations from astrophysics combined with particle experiments provide complementary information about this process. Dark matter remains one of the most significant mysteries in modern science. Although protons make up ordinary matter, they represent only a small fraction of the universe's total mass, energy content. Observations suggest that most of the universe consists of dark matter and dark energy, which do not interact strongly with electromagnetic radiation. Some theories propose that dark matter may interact weakly with protons through rare processes. If such interactions could be detected, they would revolutionize physics. Experiments around the world are designed to search for weakly interacting massive particles using highly sensitive detectors buried deep underground. Technology will also play a crucial role in future proton research. Advances in computing allow scientists to simulate proton structure using lattice quantum chromodynamics. These simulations break space and time into discrete grids and calculate quark-gluon interactions numerically. Supercomputers are required because the equations of quantum chromodynamics are extremely complex. As computational power increases, simulations become more precise, allowing scientists to test theoretical predictions against experimental data. Future particle accelerators will reach even higher energy levels than current machines. These accelerators may recreate conditions similar to those just after the Big Bang. By studying matter at such extreme energies, scientists hope to discover new particles, additional dimensions of space, or new symmetries in nature. Some theoretical models suggest that protons may reveal evidence of supersymmetry, a proposed extension of the Standard Model that predicts partner particles for known particles. The proton also plays a role in future energy technologies. Nuclear fusion research seeks to replicate the proton fusion processes that power stars. Fusion reactors aim to combine hydrogen nuclei under controlled conditions to produce clean, nearly limitless energy. If successful, fusion technology could transform global energy systems. Understanding proton behavior under extreme temperature and pressure is essential for achieving practical fusion power. Philosophically, the proton continues to challenge humanity's understanding of reality. The journey from classical physics to quantum mechanics showed that nature is not always intuitive. Future discoveries involving protons may further alter our understanding of space, time, and causality. Some physicists speculate that spacetime itself may emerge from quantum information processes. If this is true, protons and other particles may be manifestations of deeper informational structures rather than independent physical objects. Another fascinating area of future research involves precision measurements of proton properties. Even tiny deviations from predicted values could indicate new physics. Scientists measure proton mass, charge radius, magnetic moment, and scattering behavior with extraordinary accuracy. Each improvement in measurement technology opens new possibilities for discovery. The proton serves as a natural laboratory for testing fundamental physical laws. The proton also has technological importance beyond fundamental science. Proton therapy is becoming an important tool in cancer treatment. Because protons deposit most of their energy at specific depths inside tissue, they can target tumors with high precision while minimizing damage to surrounding healthy cells. This medical application demonstrates how fundamental particle physics can directly benefit human health. Looking forward, the study of the proton represents a broader quest to understand the universe at its deepest level. Scientists hope that future discoveries will lead to a unified theory of physics that combines quantum mechanics and gravity. Such a theory would explain the behavior of matter across all scales, from subatomic particles to cosmic structures. In conclusion, the future of proton research is filled with possibility. From searching for proton decay to mapping internal structure, from exploring cosmic origins to developing new medical technologies, the proton continues to shape scientific progress. It stands as a bridge between known physics and unknown reality. As technology advances and experimental methods improve, the proton will likely reveal even deeper secrets about the fundamental nature of the universe. The journey into the heart of matter is far from complete, and the proton remains one of humanity's most powerful tools for understanding existence itself.